Then I have squared 0.88 amps squared over 12. 0.88, let's call it 0.90. 0.90 squared is
0.3.
point
0.3. 0.0.
Point 8 amps squared. 0.8 divided by 12, 65 milliamps squared, something like this. It's absolutely negligible. Can you make this calculation for me, please? 25 is probably, the result is probably 5.0005 or so, 6.
5006.
5006. Is it so different from 5? Is it worthwhile to waste your time like this? No, never. So. And, you still have to add the switching frequency for your inductor is 200 kHz. And that should be enough to choose from a catalog of your inductor component. Most of the time, the inductor is already manufactured and available on the market. So far so good? Now, let's go to choose diode and switch. Diode. This is easy. Because we need voltage and current for our diode. Let's say that the diode current, TID, is something like that. Do we know what's the maximum absolute value of a here? It's still the same. It's 5.44 amps. And the value of here is, who cares, 4.56 amps. How long is this interval?
1 minus 1.
That is 1 minus d, possibly divided by switching frequency. It depends if you want the real time in microseconds or if you want the normalized time. Normalized time is fine. So, for a diode, we need to specify two numbers, maybe 3, plus a category of diode. And the numbers are ID average, ID peak. Do we need ID RMS? No. But I put here ID RMS just to make some RMS. Just to make some training on using the flat top approximation. We will use the RMS current to a diode later on in more complicated topologies, not here. ID average. How much is the average of this waveform? That means take this area, spread it over one cycle, and see how much, how high, how tall is this value when you spread it.
I know.
We can say that the trapezoidal area is equal to the area of a rectangle that has a height and an average between the 2 points. And this current is 5 amps. I know. So ID average is just equal to 5 amps. Let's say I naught times 1 minus d, that is 5 amps, times 1 minus 0.43. I use the minimum duty cycle because I want the maximum current, the average current of the diode. 5.57.
Zero. 85.
Okay. Random numbers.
85.
5 point?
2.85.
Oh, 85. I was hearing 55. 85 what? Amps. This is the average current. The maximum average current. Does our diode conduct this average current all the time? No, only if the duty cycle is minimum. If the input current, if the input voltage decreases, duty cycle will increase to keep the output voltage constant, and so if the duty cycle increases, my stress and diode will decrease. But this is the worst case. ID peak, well, is there 5.44 amps. ID RMS, we don't need in this case the RMS current to the diode, but just to see if you remember the flat curve approximation. Is the RMS value of a square wave having this duration, this width, and the height that is the average between the top, the peak, and the lateral. And this average happens to be output current. So ID RMS is just I naught times square root of 1 minus d. Minimum or maximum? D. Minimum, because I still wanted to get the maximum stress to my diode, equals 5 amps times the square root of 0.57. How much is the square root of 0.57? Point 75, close enough, yes. A little bit more than 0.75. And 0.75 means 3/4 of 5 amps. That means a little bit less than 4 amps, 3.8 amps. How much? 3.77 amps. Do you need this number? No. Unless you are using very large diodes. We are not talking about a 200 kilohertz, 60 watts buck converter. We are talking about 1 megawatt converter. For high current diodes, you need both average current for the stress, for the conduction losses, and RMS current, because the contact resistance, the wiring resistance, is so important for these high current diodes that we also need the RMS value. This is just to see if you remember how to use the flat top approximation. This is an approximation. It's not right, but it's very close to the actual value. Okay, we have for our diode current, average current, peak current, RMS current, and we need voltage. What voltage do we need? Well, voltage we need for a buck converter, for a diode, what's the maximum voltage this diode can see across it? The voltage that this diode sees across it when it is reverse biased, it's basically the input voltage. Because if the input voltage, when the switch is closed, the input voltage is applied directly to the diode. And so, the maximum voltage this diode is experiencing is 28 volts. Let's suppose that you find a diode that has a rating of 28 volts. Do you pick it? No. No. Better to stay a little bit wider Let's suppose you see a diode that has a rating of 40 volts. You take it? Yeah, should be okay. 40 volts, if the input voltage is maximum 28, it's okay. What if this goes to, in a car, in a truck, when the voltages over here are on average between 20 to 28 volts, but you can have spikes, you can have over voltages, short duration, but over voltages up to 50 volts, 80 volts or so. If you don't have any protection over here, this diode will die, and the MOS transistor as well will die, unless you use to 100 volts parts. So 40 volts, if you have protection, is okay. If you don't have protection, put that. If I remember, I will put online a link to an application note showing what are the maximum voltages you can have in a car, or the maximum voltage you can have in a house due to the lightning, to the electric thunderstorm around, etc. Anyway, diode. We have currents, so we have I diode average equals 2.85 amps. I diode peak equals 5.44 amps. VD reverse equals, let's say, 40 volts. That is our choice. This number, this value is normalized, but it's not normalized with the standard resistance values, 10, 12, 15, etc. Those are, in some cases, normalized according to the, for the capacitor, to the R5 series. In other cases, you have to go to the catalog. For Schottky diodes, by the way, 40 volts, we can use a Schottky diode. Schottky diodes means you can have 20, 30, 40, 50, 60, 80, 100 volts or so. More or less the resolution is different. If you want, at this point, you can estimate the dissipated power of your diode. How much power does your diode dissipate? Diode has a voltage drop across it that is almost constant. It does not depend too much on the current. So you can see that the power that your diode loses is about something like the voltage drop across a Schottky diode. How much is it? 0.5, 0.6, depends on what diode you choose. 0.5 volts times 10. What current do we need?
Medium current is the average.
Average current. Because the power, what we need is the average power, the average dissipated power. When we take the average dissipated power, the constant voltage moves out from the integral, and you are left with the average current, 2.85 amps. 0.5 times 2.85 amps is 1.5 watts. It's about 1.5 watts. I know that 0.5 times 2.85 is 1.425, but it's useless. 1.5. It's a power, it's thermal power. And you are not sure about this value. Absolutely sure about this value. Okay. Our diode is gone. Three numbers for that. Average current, peak current, and reverse voltage. If it is a Schottky diode, if it is a silicon carbide diode, a Schottky diode, your diode is intrinsically fast, very fast diode. There are no minorities. If you choose a standard diode, PN diode, for example, because your reverse voltage is 200 volts, so you need a standard diode. You can't use a Schottky diode. If you use a PN diode, you cannot take the first diode you find in on your bench, workbench. You cannot find any diode like, for example, 1N4007. You know, 1N4007 diode is everywhere in any level. Well, this is too slow. You need a very fast recovery diode. dial for switch mode, not any dial. If you put 1N4007 whatever in a switch mode converter, your converter will just gulp it, literally. E non sputa neanche gli ossicini. Dials. If it is silicon carbide or Schottky, it's basically fast. If it is standard, you have to specify that must be a high speed dial, faster. Switch, MOS. Most of the time we use MOS transistors in this class. So for the MOS transistor we need the IRMS, because an MOS transistor when it's on is basically a resistance. We need I peak. We don't need directly I average, because the average current to a switch is important when the switch has a constant voltage drop. So for a bipolar transistor, I average is important. For an IGBT, I average is important. For an MOS transistor, IRMS is better. But we will find this value as well. And then VDS when it is reversed biased. The maximum when it's off, so VDS when off. Plus we will need one extra step. IRMS. Oh, IRMS means that this is an IMOS, a switch time. This is my current flowing through the dial. I know that this peak is still the same. It's always there. 4 point meaning 5.44 amps. Do we use the flat top approximation over here? Yes. Sure. If we use the flat top approximation, how much is this flat top value?
5 amps.
Still 5 amps, I know. So, IRMS, if we use the flat top approximation, equals I naught times square root of t, because this duration, this length, is t. Equals 5 amps times square root of
0.6.
the minimum or maximum will decide. I want to find the maximum stretch, so I need to use the maximum to decide. Oh, I don't know the maximum to decide. I didn't find it yet. T equals V naught over V in equals 12 volts divided by 20 volts.
0.6.
0.6 volt. They measure this. 0.6 equals, how much is the square root of 0.6? .77, 78. Point 0.77 times 5 amps is 3.87, okay, 3.9 is close. 3.9 is close. RMS current through the MOS transistor is 3.9 amps. Should I write here 3.9 amps RMS? No. It's a no, definitely. Don't even dare tell me about RMS current, RMS amps, peak volts, and something like this. Volts per volts, amps as amps, is the voltage that is peak or RMS, the current is RMS, etc. 3.9 amps RMS value. IP equals 5.44 amps. I average do you need the average current for an transistor? Not to determine its losses, but we find it anyway. Average current for the MOS transistor equals I naught, is the average of this waveform. I naught times D. How much is I naught times D? 5 amps times 0.6. That is 3 amps. Okay, those are all the currents through the switch. Why do I need, no, I don't need actually. Why I want to know this current? Because, let's go to the schematics. The average current flowing through the switch is coming from D. So, if I know this input current, and I multiply this input current times the input voltage, what do I get? The input power. So I found that the input current is 3 amps when the input current is the input voltage is 20 volts. 3 amps times 20 volts is 60 watts. How much is the output power my converter is designed for? 60 watts. It means that I didn't make too many errors. Is it true? Is it possible that I get 60 watts here at the input? No way. It's impossible to have 60 watts at the input and 60 watts at the output because the efficiency is not 100%. It's not long. Input power will be a little bit larger than 60 watts. And it will be a little bit larger than 60 watts because the duty cycle, the actual duty cycle will be a little bit larger than 0.6. But as long as these two numbers are very similar, I am fine. I am happy. If your input voltage turns out to be 33 watts, input power turns out to be 33 watts, and your output is 60 watts, you made some bad mistake somewhere. Check. Or you invented the perpetual motion. Lucky you. But it's not going to happen quite easily. So if you find the input power that is less than the output power, there is something wrong in your calculation. On the other hand, if you find an input power that is 900 kilowatts and the output is 60 watts, guess what? You made some bad mistake, really bad mistake. I had a student once that the final exam, in order to design a 200 watt converter, found out that the input power was 1.8 megawatts or something like this. And he wrote it down 1.8 megawatts without the blade. And he said, no, you needed to study a lot more to become an engineer. And he failed the exam. Guess what? If
we consider the maximum being,
yes,
we have not more the efficiency, maximum efficiency of 1. So if we consider the ideal conditions, if we may have anyway the efficiency.
What happens if instead of 20 volts we consider here case of 28 volts? There's the question, because it seems that 28 volts times 3 amps give you a lot of power. Whatever. Is it right, this calculation? No.
We have to change the error.
Because if the input is 28 volts, the duty cycle won't be 0.6, it will be 0.43. And if it is 0.43, the average current will be 5 amps times 0.43, that is 2.15 amps. 2.15 amps times 28 volts, guess what? It gives you 60 watts again. Is it the answer to the
Yes,
question?
thank you.
Oh, by the way, question just remind me that I forgot to tell you one. What's the maximum, maximum power dissipation for an MOS transistor depends on the RMS current, because it's a resistance. An MOS transistor, when it's on, it's a resistance. So, the RMS current will be this one. And with this RMS current, I can find out how much power I waste on my MOS transistor. The maximum dissipated power by a diode is given by the average power, the average current. The average current for the diode is this one. With this expression, I can find out how much is the average dissipated power from the diode. With this expression for the MOS transistor, I can find out how much power I dissipated, average power I dissipated to the MOS transistor. There will be some extra, but we will find later on. So, can I add the power lost by the MOS transistor in these conditions with the power lost by the diode from this condition? No, these two conditions are different. Because I found the maximum diode current, that means the maximum power dissipated by the diode, using the minimum. I found the maximum RMS current flowing through the switch using the max. You cannot add these two quantities together because they have been evaluated in two different conditions. One the max, one the min. It's not too bad if you add that then it's not too hard. Okay, what is the voltage across the MOS transistor? When the MOS transistor is obviously open. Well, when the transistor is open, on the right hand side you have negative VD. On the left hand side you have VD. V minus negative VD is VD. So this transistor has a maximum voltage across it when it is off of 20 volts, 29 volts, something like this. And so the MOS transistor undergoes to a voltage stress VDS max, that is about 8. Oh, by the way, if you just home your truck, you can have a glitch, a voltage glitch that goes up to 50 volts. So if you pick a 40 volt MOS transistor and you have a 50 volt glitch, your transistor is not too happy. Put protections in front of it. This capacitor acts as a protection. It's not the best you can have, but better than not. But put your protection, because in a buck converter, MOS and diodes are on the front line. Anything that comes from the supply goes directly to the switch and to the diode. So if you have an over voltage over here, the two components are the first to fail. Diode and MOS. Okay. Unfortunately, numbers we found MOS, we found VDS max equals larger than 28 volts. Let's say 40 volts or so. IDP equals 5.4 amps. ID RMS, nothing, MOS. IMOS RMS, how much was it? 3.9 amps. That's it. Those are the important numbers I told you. Well, these numbers are not enough to choose the diode. And the MOS transistor. MOS transistors have two important specifications when you go to the catalog to look for a suitable part. And these two important specifications are VDS max, and on the catalog you find it's indicated as VRDSS. This is the symbol you find on the data sheet. And is the maximum voltage that the transistor can sustain when it is open across it. And this is the number we found over here, 40 volts. And then, usually, in power electronics, nobody cares about the RMS current and the peak current to the MOS transistor. The important parameter is a different one, and the important parameter is the so-called RDS on. That is the resistance the channel your MOS transistor has during the on phase. During the on phase, your transistor looks like a resistance. The value of this resistance is given by RDS on, and is an important parameter in your design. You have to specify these two numbers. Those are the most difficult requirements, constraints to satisfy. Once that you have a reasonable RDS on, you check the current, and the current is more than this, almost always. How do you choose the RDS on for an MOS transistor? Let's go to our circuit again. This looks like, when it is on, like a resistance. How much current flows through this resistance? Current flow through this resistance is a standard switch current. I switch, that is something like this. Peak value is 5.4 amps. Flat top value is 5 amps. What happens when you have a current flowing through a resistance?
We have a voltage drop.
Voltage drop. This is the requirement. How much voltage drop are you willing to accept across this MOS transistor?
Comparable with the diode.
Comparable to the diode voltage drop? Well, you can do better. Because the diode voltage drop is a half a volt. You can go lower than this.
1 order of magnitude lower.
Say again?
1 order of magnitude lower.
1 order of magnitude lower of what?
With respect to voltage drop across the diode.
Oh, 1 order of magnitude lower than the voltage drop across the diode. So you say, I won't have to worry about this voltage drop. Well, it could be okay, but situations in which buck converters can work is quite different. Having a voltage drop here that is quite lower than this voltage drop is okay. It means I have at least one good switch. But what is important is that this voltage drop is in series with the input voltage. This voltage drop is subtracting to the input voltage. So if your input voltage is 300 volts, just an example, and you drop 1 volt over here, that's okay, who cares? It's less than 1%. If your input voltage is 3 volts, and you drop over here 1 volt, you are wasting 30% of efficiency just here across. 1/3 of your input voltage is lost just across your switch. So, a better idea to determine how much voltage drop you want across the switch is to say something like, voltage drop that is small, quite smaller, couple of order of magnitude less, and then the input voltage. 1 order of magnitude at least, maybe 2. Because remember, if here you lose 10% of the input voltage, you have 10% of your efficiency flying away from the window. Lost, just that. So if the minimum input voltage over here is 20 volts, and you put here a voltage drop that is 1 volt, 5% of efficiency is lost just on this switch, just on the voltage drop across the switch. The voltage drop across this switch should be at least, well, it depends how much power you can dissipate, how much efficiency you can lose, you accept to lose. But it could be a few percent of the input voltage. So 20 volts is the minimum. Here you could have, let's say, 0.2, 0.3, 0.4 volts, something like this. So it means that you will have 1%, 2% of efficiency lost just because of this resistance. You could say, okay, I can pick a very good MOS transistor, an MOS transistor that gives me a voltage drop over here that is only 1 millivolt. Is it good? 1 millivolt of voltage drop means that your efficiency loss is negligible. 1 millivolt out of 20 volts, you don't see it, you can't even measure it. But if you take a very large transistor, a transistor that has a very small RDS on resistance, you have two disadvantages. First, you need a lot of silicon. A lot of silicon, a lot of area of silicon requires a larger package, and package is cost. Cost is not given directly by the silicon, it's given mostly by the package. The larger the package, the more expensive is the your component, with some exceptions. Second, if you have a large silicon area is related to parasitic capacitances. And if you have a large capacitance, looking into the gate, you have to charge and discharge this large capacitance every time you switch it on and off, 200,000 times per second. So, choosing a very large component here requires a lot of money, because a large component means more money, more expensive, and it requires a very strong driving circuit, because in order to drive a large capacitance, you need to provide a lot of current. So don't overkill your problem. If you overkill your problem, usually it's wrong, because you pay too much. Voltage drop that is in the order of a few percent of the input voltage, it's probably acceptable, except in very rare cases. So, we need to find out how much is the RDS on, because RDS on is the second important parameter. These two parameters allow you to choose an MOS transistor, not the current. RDS on is the resistance, and as any resistance is given by the ratio of voltage divided by current. What voltage? The voltage across this resistance. That is VDS on the voltage that you allow to drop across your switch divided by IB max. That is your choice, your call. How much did we say? 0.2 volts, 0.3 volts, something like this. 0.2 volts divided by ID max. How much is ID max? You can put 5.4 amps, or you can put 5 amps. Nothing changes. Let's put it 5.4. Turns out to be something like 37 millions, 36 millions. Oh, by the way, this is the important number. When you go to pick an MOS transistor that has a maximum voltage across its 40 volts, an RDS on 37 million, you will find that your MOS transistor can carry a current that is far, far larger than 5 amps. Unless you take a very small package. In some cases it can be limited by package. Not specific. Okay. Who among among you, that means everybody, owns a car. Chissà che cosa ho chiesto. Everybody owns a car. What car do you own? Pan. What's the power?
1.5 kilos equity.
No. What car do you own?
Clio. Old
Old?
Clio.
Or Clio? What's the power?
50 horse or less.
How much?
The engine?
Yeah. Engine power.
60 horse, 40 horses.
4 HPs, 60 HPs, horsepowers.
Horsepowers?
Yeah, 60.
Yes.
Okay. Horsepower. Is it a unit, an allowed unit, a permitted unit for power? No, you can't use horsepower. Horsepower because it's outside the international system. You should use kilowatt. Unfortunately, kilowatts are a little bit larger than horsepower. Horsepower is about 3/4 of a kilowatt. So instead of saying 60 HPs, you should say 40 kilowatts. But 40 is a small number, does not look good for cars. So car manufacturers still use HPs because they can give you a larger number. Well, here in the MOS data sheet, there is something similar, not so blatantly bad, but the RTS on that you find in a data sheet has a small note and read the fine print interface at 25 degrees Celsius. When your transistor works, it won't be at 25 degrees Celsius. It will be, for example, at 80 degrees Celsius because it dissipates power, it heats up. RTS on is a function of temperature. And guess what? If the manufacturer tells you the resistance is 25 degrees Celsius, it means that at this temperature, this resistance is smaller than the resistance at 80 Celsius. What I mean is that you will need 37 milliohms when the transistor works, when it is hot. This is the hot resistance, RTS on hot. But on the data sheet, you find a better value, you find a better number because it's given at 25, it's cold resistance. And the cold resistance can be 70% of the hot resistance, can be 1/2 of the hot resistance. So if you get the 37 as your design requirement, don't look for a 37 billion on the data sheet, because the data sheet, the manufacturer makes the same trick as the car manufacturer. It gives you the good unit, but in conditions where the transistor is not working. At 25 Celsius, the resistance is quite low. So if you need a 37 billion when it works, look for 37 billions divided by a safety factor, not a safety factor, factor that goes from 1.5 up to 2. So look for a 20 million, 25 billions part. There is a graph that tells you how much is the actual resistance when the silicon heats up. But the first number that the manufacturer tells you is a small number. Looks better. Okay. We still need to take something consideration about capacitors after the fact. And having the rate a little bit bright has an advantage.